Hi there. Now that we've discussed many older attacks and defenses, I'd like to also give some attention to some of the newer work that we've been doing to get some idea of what kind of work is being done in research right now. One very good example is Blindside, which is a very cool project that combines some of these hacking techniques that work on software vulnerabilities with hardware vulnerabilities related to speculative execution. Now, the idea of this project, Blindside, is that it combines two earlier projects. It combines Spectre attacks, which are attacks against the hardware vulnerability, with hacking blind, which is an approach to bypass ASLR using a program that can resist crashes, essentially probing again and again to figure out where the data is. Now, Spectre attacks use speculative execution, whereas hacking blind requires crash-resistant programs. Now, Blindside allows you to do the same thing as hacking blind, except that you don't need the program to tolerate crashes. So rather than tolerating crashes, you use a speculative execution attack, which will be rolled back by the CPU anyways. So this makes buffer overflows more powerful because now we can use the hacking blind approach even in cases where the required primitives are not available. Before we continue to the explanation of Blindside itself, I'd first like to explain a little bit how the Spectre vulnerability actually works so that you have some of the required background. Now, to understand the Spectre vulnerability, you first have to understand how modern CPUs work. Now, modern CPUs require deep pipelines for performance. A deep pipeline means that the CPU simultaneously executes many instructions, but in different steps of execution. So some instructions might be decoded, others might be doing the arithmetic, whereas still others are being effectuated by, for example, writing back results to the registers or the memory. So there are many instructions executing at the same time, and this is actually necessary for performance. We have many transistors available and we need them to do some work. And by having them all do one of these tiny steps of the pipeline, we can parallelize the execution and make the transistors do more work. Now, if we need to wait for a full instruction to finish, this causes a lot of overhead, because this means that the pipeline will become completely empty while waiting for knowing what the next instruction will be. Now, this is something that you don't want to do, so CPUs all implement some way to deal with this situation, and they do it by predicting what the next instruction will be. So there is branch prediction, which uses a cache to basically store what happened in recent indirect and conditional branches. So for indirect branches, you would store the recent targets of the branch and then use that to infer what might be a likely next target for the branch. And in case of conditional branches, you keep track of whether they are taken or not taken and apply the pattern of this to predict the next one. Now we continue executing along the predicted path, but speculatively. Now if it so happens that the speculation is correct, we just continue as if this was a regular execution. However, if it turns out our speculation was incorrect, that is, we expected a different branch target, then we have to roll back execution and go back to the point where we got it wrong, and then take the other path. So this means that branch prediction can do a lot to make sure that the pipeline is filled at all times and the CPU performs adequately. However, it also introduced a vulnerability. So the Spectre vulnerability is found in many Intel CPUs. It was disclosed in early 2018, so it's a relatively recently known problem. You may remember it from the news stories. And even today it affects many systems. Now, what is the issue here? The rollback is incomplete. So the CPU speculates on taking a particular path, execute the instructions along those paths, and then rolls back changes such as, for example, changes in the register. However, it doesn't erase the invisible state. This means, for example, that memory which is read remains in the cache. Now, accessing this memory again will be faster than if the CPU hadn't executed this speculative path. So it's possible now to derive from other memory reads and writes what information was actually being accessed. And this can be used by an attacker. The attacker can train the branch prediction to expect a certain path to make the CPU mispredict the path. The CPU will execute the program and will speculatively execute the path designated by the attacker as the most likely path. And next, the attacker can determine, using timing of memory accesses, which memory was actually accessed along the speculative path. Now, in certain cases, this allows the attacker to derive hidden information from the execution. This is a typical example of a Spectre gadget. Now, there are multiple versions of Spectre, and they relate to the kind of cache that you're corrupting. So there's different types of branch predictions. For example, conditional branches or indirect branches, and they use different tables to cache recent accesses. Now, Spectre v1 means that we're talking about conditional branches. So the CPU keeps the history of whether a branch was taken or not. Now, if we look at this if statement, now this is a very typical thing that you see in programs. You see a bounds check that verifies whether an index is in bounds, and then you access some data based on that index. Now, this is a very common pattern that you'll find all over programs. Now, what is the issue with Spectre here? If the attacker trains the CPU to expect that the index is in bounds, it will speculatively execute this path and dereference a pointer that's not in bounds. Now, at this point, we get no information yet. So the CPU has loaded the value, but we already knew where to expect this value, assuming we know the index and array 1. But typically, we would be able to influence the index in this particular case. Now, the next step is where Spectre becomes interesting. What if the data that was loaded is used as an index into another array? This is also very common, and this is where Spectre can easily be exploited. So in this case, the memory that is accessed depends on the value that was read. This is very common, and it means that we can derive the value that was read by checking out which part of the memory is in the cache now. Well, Spectre v2 is about indirect branches, and it means telling the CPU that an indirect branch is going to go to a particular address, right? So in this case, a typical gadget is very simple. It's a call instruction, and we try to get the call instruction to call some other function by training it to do so. Now, this is a very effective attack because it means that we can speculatively execute any part of the program where we can train the CPU to think that the program is going to go. So this is a very strong attack, and any cache impact of the code executing at that location can be used to infer information about the program. Now, there are some mitigations available for Spectre, but the ones that are deployed in software are pretty high overhead. So for example, what we can do is mask user controllable indexes. This is an effective solution. It means simply applying the AND operator, for example, to make sure that the index cannot go out of bounds or not too far out of bounds. Because in this case, it doesn't rely on speculative execution. There's no branch there. The masking is actually always applied in the speculative path, and the data access is safe, or at least more safe. Another is using a red polyne, which is used to change the instruction that performs the indirect call, to change it in such a way that the CPU can no longer speculate on the indirect branch. And finally, hardware protections are also an option. So hardware protections can be deployed either by getting newer hardware in which this problem was fixed, or updating your old hardware. But of course, there's still a lot of vulnerable hardware out there, and it's a very widely it very widely affects available hardware in the field. Now, the blindside attack combines Spectre with hacking blind. So I will give a very brief explanation of how hacking blind works so that you can get some idea. I won't explain all the details, but the idea is simply this. If we have a program where we cannot leak information or not leak enough information to be able to break ASLR, then we need to use another solution. Now, hacking blind is one of these solutions. And what it assumes is that we have a so-called crash resistant program. Now, crash-resistant programs are actually very common. So a crash-resistant program is the situation where we can cause an exception, such as a segmentation fault, and still the program continues to execute without re-randomizing ASLR. A very typical example would be a web server. If we crash one of the workers of the web server, then it will simply spawn a new one. And this is necessary to ensure availability, even if there's a bug in the code. So it spawns a new one, but this new worker program is still executing the same program. So the program forks and ASLR is not re-randomized. Now this means that we can probe the memory. We corrupt some stuff using a buffer overflow, see what the impact is. So in the response we can typically see whether the program has crashed or not. And now using these side effects, such as whether the program has crashed, we can determine whether, for example, we accessed some memory that was actually available. Now this is an effective way to de-randomize ASLR. However, this approach has the limitation that the program must be crash resistant. And not all programs are crash resistant, and moreover, one of the most valuable targets, the kernel, definitely is not. If we make the kernel crash, it means that the system will reboot, and then every random thing will be re-randomized, and it's pointless. So, what we need to do instead is find some way to replace the crash-resistant primitive with something else. And of course, as it turns out, something else in this case is Spectre. Now that we have this idea, it becomes relatively simple to do a blindside attack without a crash-resistant primitive. What we do is we use a buffer overflow to corrupt the function pointer, but now we don't execute the code directly, because if we got it wrong, the program will crash, but instead we execute the function pointer speculatively. So we fool the CPU to make it jump to this instruction pointer, and when it jumps to the function pointer, we can determine what the side effects are. So if we see the side effects in the cache, we know that the function was actually executed successfully. If we cannot see the side effects, then presumably the speculative execution crashed. In this case, because it's speculative, it doesn't result in a segmentation fault, but we can tell the differences from the state of the cache. So this means that we can now perform the same thing as hacking blind did, but without actually crashing the program, which is a much more powerful primitive than what we had before. So now if we combine the example gadgets that we had for Spectre, V1 and V2, what we get effectively is the ability to cause a misprediction, as well as the ability to execute an indirect branch conditionally. Now, because this is a misprediction, it will be rolled back eventually, and any crash will not be visible in the end, even though the impact on the cache actually is. So it should be obvious at this point that this is a super cool idea, but then the question becomes, does this actually work? Are these gadgets actually available? Or is this a super rare situation that we cannot really use? So what the researchers in this project did was take a look at the code that's actually out there and investigate whether there are any plausible gadgets for blindside that can perform such an execution. Now what we need, as I said, is a situation where we can conditionally execute an indirect branch. Well, when we looked at this, it turns out that actually 50% of all the indirect branches, so that's a lot, actually have a conditional branch within a distance of 50 instructions. And in fact, if you look closer, it turns out that even if you look within a distance of 5 instructions, where a speculative execution is very likely, then even still 37% of all the indirect branches actually have a conditional branch this close. So this means that there are many plausible gadgets out there in real programs. Our group actually implemented this approach and used a real CVE reported vulnerability to see if we can use it to exploit the Linux kernel. Now, we managed to make three exploits using these primitives. We managed to break kernel ASLR, so figuring out where all the code and the data in the kernel is. We managed to leak the root password from the data structures in the Linux kernel using a data-only attack, so without corrupting any of the control flow in the Linux kernel, which means that this attack is actually resistant even to CFI. And we managed to leak kernel code. And we can do this even in case of fine-grained randomization, so fine-grained ASLR, plus software-based execute-only memory. So we have a very strong primitive here that allows us to completely de-randomize the kernel and leak data without even changing the control flow compared to what is allowed. So we've been able to use a Spectre gadget that's been available in the Linux kernel for a long time. So these gadgets are out there. As in terms of software, they're not actually vulnerabilities, because these are actually very normal code constructs. And as a consequence, you can see that they remain in there for a long time. People see no reason to remove them, and as such, they're widely available. So what I've shown here, I've slightly condensed the presentation, so not all the material was in there, but I've shown how a modern attack can actually use modern hardware attacks like Spectre and combine them with existing software attacks like hacking blind to make a much stronger exploit primitive. Now we managed to use buffer overflows to hack blindly, even in cases where a program crash kills the system, such as the kernel. Moreover, we have shown that mitigations that are available in modern systems are not effective here. And we mentioned some of the mitigations that have been discussed in this class. So this is a very powerful, interesting, and new attack primitive. And it shows how even existing defenses make it very hard to completely secure a system against a determined attacker.